I want to welcome you all to this event. I'm Christian Borgs, I'm the director of BIDMaP, and we are running this event together with the Berkeley Climate Lab. I will not talk that much about it. I think Dave will introduce what that does tomorrow. BIDMaP, I will just say 2 words. It's an institute which is at the boundary of AI and materials. So we bring together professors from chemistry and material science and people who do computation, and we study materials to help with climate. And this is the theme of this symposium, from the academic research to startups to implementation. I don't know whether we have some funders here. If so, I really look forward to work with you funders to help us address climate. We all need to work on that together. And let me see. Okay, so we have a broad audience. We have researchers and students from academics. We have some startups. We have VCs, as I said, and I hope we all interact with you and you keep interacting with us after this event. That's one of the reasons why we run something like that. There is a little thing you can scan on your phone to connect with us. And there also, during the breaks, there will be a desk hosted by our postdocs. You can go and talk to those. If you are a student and you want to engage, maybe later we have a young scholars seminar organized by the postdocs. If you want to engage with that later, you can talk to our postdocs. So I encourage you to interact a lot in all our breaks. Okay, with that, to the program today. Today we do 2 sessions on AI for materials. The first one will be on AI for energy materials, and the second one will be on AI for carbon capture materials. And our first session starts now. Mark Aster, who is one of our deans. So normally people use postdocs and students as moderators. We decided to take the 2 available deans of the So Mark will be the first one. He is a material scientist, and with that, I give it over to you.
Okay. Yes, thank you all. I apologize in advance for being a dean and a moderator. So thank you, Christian. So yes, so this first session, we have 3 great talks lined up that will really give you a perspective on how AI is being used from the simulation, computational side, through the experiments to the autonomous labs, all in the context of energy materials. So I think it's going to be a really great set of talks, and will really cue us up well for a good panel discussion. So the way we're going to organize this is we're going to have 3 talks in a row. No questions or answers after the talks. We'll reserve the questions for the panel session, which will come at the end. So whatever questions you have, write them down or something so you remember them, and then we can bring them up. There will be audience participation during the panel session. Okay, so without further ado, let me introduce the first speaker. This is Jeff Neaton, and he is local here. He's a professor in physics here at UC Berkeley. He's also a senior faculty scientist in the Material Science Division of Lawrence Berkeley National Lab, and also the associate lab director for energy sciences up at LBL. Jeff has worked for quite some time in the area of materials theory and also computational materials science, and has really done a really pioneering work across a broad spectrum of materials, often with really understanding nanoscience, dimensions of energies and how they perform. So he's been recognized by many awards for his work, including up at Lawrence Berkeley Lab as an Outstanding Achievement Award, and he's also the Presidential Early Career Award for Scientists and Engineers recipient during the early career part of his research. So he's also a fellow of the American Physical Society, and so I'm going to hand it over to you, Jeff, without taking away more of your time, and thank you very much for agreeing to come in. Jeff kind of agreed on Monday to participate, so we really appreciate that. And there's a clock there.
Okay. All right. Well, thank you very much, Mark. And yeah, it's wonderful to have this opportunity to speak at this event, and a lot of great sessions and talks. So perhaps due to the last minute nature of this, one of the vignettes I'm going to show has some overlap with another part, but I think that'll probably be okay. So I'll speak a little bit about energy materials research that we've been doing. My background's in computation, as Mark said. We've been using machine learning, so that's probably the connection to AI. But I'll tell you a little bit about that research. And let's see here. Okay, I like this. Yeah, pointer. So I think just as I don't have to tell this audience, I don't have to say this to this audience probably, but we are kind of in an era where I think we are seeking energy abundance. We are, if we're thinking seriously about AI, we're going to need as much energy as we can get, actually. And that includes very much, and I think dear to our hearts, renewables and clean energy. And so this is a cartoon from an article several years ago by Steve Chu and coworkers about different energy kind of sectors, some of which are quite underdeveloped. For example, solar fuels, I'll mention in a second. And I think one of the kind of almost cliched things we could say is that new materials are sort of central to all of these technologies, but none of these technologies is perfect in terms of cost, efficiency, or durability. And so even more mature technologies probably could benefit from new materials research. Now, one of the ways we have been doing research over the last decade or plus, or actually more than that, is to use and integrate increasingly computation into understanding materials performance and also discovering new materials. And I wanted to start with an example of some work that we've done in the several years ago, actually, in this area of solar fuels. This is just a slide on this. And so in this area of artificial photosynthesis, so kind of trying to do what a leaf does, reduce CO2 in the presence of sunlight into high energy C products, but with, instead of a leaf, organically with an inorganic set of materials. And so actually such stacks exist, and particularly for water splitting, which is part of this process, you can get up to like 20% or so. You might want to, but it is worth doing this efficiency. It's worth doing this because natural photosynthesis runs at about 2%. And so there is some advantage, and to kind of looking into this. And so this stack of materials that would kind of mimic some of the processes inside chemical processes in a leaf don't have to read any of this, but there's several materials here, and all of them have different function. And basically, we're looking at one of them in particular and trying to improve them, and that's the material that interfaces, that kind of undergoes water oxidation or helps with the OER process, a so-called photoanode. And this is work I did with Christine Pearson and John Gregoire. And essentially what we were able to do is working closely with the experimental group, John Gregoire, and using the materials project, which is a database of DFT calculated properties of lots of different materials. We were able to kind of scan for some bulk, some bulk properties that would make for a good OER photoanode, and then come up with a proposal for about 34 of them. And John Gregoire's group managed to make 12 of them in the lab. And so actually at the time, there were only kind of 12 photoanode materials known. So in this study, we doubled the number of photoanodes that people were working with. And so we saw that as kind of as a success. However, one thing that kind of subsequently with these materials, which I won't kind of go into, was that they weren't they didn't perform all that well. They weren't the sort of best functioning performing materials. They degraded quickly. Some of their they had some performance issues, and so in terms of improving on the state of the art, none of them kind of rose to that level. And so one of the takeaways that I think is relevant for this talk is that we initially had screened for new materials based on bulk crystalline properties. And we used density functional theory, which is a very powerful computational tool to predict properties of materials that are relevant to experiment. But in practice, under device conditions, when integrated into the stack, there are non-bulk, non-perfect crystalline properties of materials that have that play a really decisive role in the performance. And so one of so DFT could give us some input, computation could give us some input into that, but because of the poor scaling of density functional theory, it can be very difficult to do such calculations of non-perfect crystals, of surfaces in contact with solvents, and all of the things that you would need to do to kind of understand the reduction in performance or to expectations. And so that has kind of been an issue and sort of a possibly an issue with this workflow of starting with bulk materials properties and trying to predict device performance. Now, why am I telling you this story? In the last, the idea that you could kind of screen with computation sort of is something that's emerged in the last 15, maybe 20 years. But in the last 10 or 5 to 10 years, machine learning has kind of come into the fore. And one of the things that's allowed us to do is study materials, but with much greater structural complexity at reduced cost, and kind of start to get at, I think, one of these central issues of screening on bulk properties when you're looking to discover energy materials. And so basically these machine learning models, which I'm going to speak about, and we are in what I would do is just tell you a little bit about these models through the lens of my own work. There's much work going on, and I think you're going to hear other panels and may have already heard panels about this. But basically, this is a class of surrogate models for density functional theory, so sort of theory that provides energies and forces based on quantum mechanics. Surrogate models for density functional theory, energies and forces, that allows you to kind of rapidly access much more complex materials that include defects or many larger unit cells, and also properties that are not related to the ground state, so not T=0 bulk properties, but in a computationally cheaper manner than DFT would do. And so this is there are kind of many reviews on this. This is one where the sort of table of content picture was the snail that shows basically DFT, and then this hair that shows the neural network model that underlies this machine learning anatomic potential. And this is sort of just to give you a sense, what we're doing here with these methodologies now is we're able to speed up the evaluation of energy and forces, and that allows us to access these much larger, more complex structures that I think, I'll tell you a little bit about some of the work we're doing in that space and the groundwork we're laying, but that could really allow us to do more than just these kind of workflows based on bulk crystalline properties. All right, so I do have a few vignettes. I will try to be short on this, and I realize that some of these vignettes overlap with another session, so I'll keep that short. But there's 3 areas we've been working in where we've been using these potentials that are relevant to energy. One is porous materials, where we're looking at carbon capture, chemical dynamics, and materials. And the other one is in optoelectronics, where we've been studying two-dimensional stacks of two-dimensional materials, so-called moire materials, and organic semiconductors. And so let me just tell you a little bit about just a few slides on each one of these. And Is this accurate for
Counting down.
counting down? But at 30, then it kind of goes, goes off. Something goes off, and smoke starts coming out. All right, yeah. So I will do better than that, I hope. So this is some work by Omar, who's actually in the front row. But basically, from him, and I think in another session you'll learn a lot more about this. Metal organic frameworks, these are kind of porous materials with very high surface area for gases to absorb. And they have some desirable features for carbon capture in addition to the high CO2 capacity, and are under exploration by many in the community, and Omar is a world leader in that. So one of the problems that we have been working on is with a local group, Jeff Long's group in chemistry, on a particular kind of MOF. This is you can sort of see this is a cutout of the crystal. This MOF has a sort of some ligands, some organic ligands, and open metal sites. These are metal atoms, these orange atoms. And basically these, so you can imagine the CO2 passing through these pores, and CO2 is exposed to these metal sites are exposed to the CO2, and they can bind to the CO2. And it turns out that is a way to capture CO2, but it's also a way to capture a lot of other gases, including water and nitrogen and such. And so so in this class of MOF, what the Long group did is they append a diamine molecule to each of the open metal sites and take advantage of the carbon amine chemistry to selectively capture CO2. And so this is a cool movie so you can take a break from my slides, but basically this is looking down the pore. Imagine you're a CO2 molecule and exploring the pore, and there's kind of amines exposed to you now, amines functionalizing the pore. And basically this is now along the pore axis. And this is, and so what happens when CO2 interacts with this environment is that it actually it displaces the amine, and there's some chemistry so that this carbon-nitrogen bond forms, and a hydrogen atom kind of hops over to the next amine, and so there's some cooperative absorption going on. And this is actually not a computation, this is an X-ray crystallography structure coming from the paper here. And so you have this kind of cooperative absorption where absorption here at this site, so insertion of CO2, that's the red and the gray here, actually makes it easier for the next CO2 to absorb on the neighboring site. And the consequence for that is that one of the metrics of CO2 capture in these materials is how much CO2 is absorbed for a given partial pressure at constant temperature, this sort of isotherm. And so what you can sort of see is a consequence of, and it turns out that it is a consequence of the fact that you have cooperative absorption. You have a so-called step-like isotherm. It's sort of like a diode for CO2. At a certain pressure, all of the CO2 is absorbed, and at another, if you back off, some of it comes out. And so that's desirable for applications, particularly if you can tune the pressure and temperature at which that happens. And it turns out that you can, if you change the chemical functionalization of these amines, you can move the pressure at which this step occurs around and basically move it into ranges relevant to natural flue gas and coal flue gas and even direct air capture. So that's promising. I mean, a lot of other attributes of this material would have to fall into place for it to be a technology, but it's interesting that you can tune this step. And it's interesting that it's kind of got this isotherm behavior in the first place. So one of the things we've been doing is using, over the past several years, using density functional theory to understand the binding energetics of CO2 at each of these sites. So using DFT, we can calculate, binding energies. We basically, construct a unit cell that kind of has a geometry very similar to the ones I showed you. We optimize it with density functional theory using kind of the old-fashioned, rigorous approach. And we find that, although there's sensitivity to the approximations inherent to DFT, there are approximations, exchange correlation functionals, that leads you to have a decent agreement with experiment between the predicted value and the measured one. And this step, the energy that is sort of absorption is kind of critical to the step pressure. It's critical to the pressure. So basically, this is a proxy for pressure. It's not a linear proxy, but it's a proxy for pressure. So as you change the energy, you're changing the step pressure. So that's an important thing to be able to predict with DFT. However, it's hard to now turn around and say, hey, here's, based on these predictions, here's a material that would do even better. That's the thing that's been a little bit holding us back. And so that's kind of where the machine learning has started to enter into what we do. And so this is a sort of, I can go pretty quick here, but this is an example of a sort of a neural network model that we're using. And so essentially in these, just a couple words about them, in this machine learning framework, what we do is we kind of write the energy in terms of the energy of the individual atomic sites, and then we express the energy at an individual atomic site in terms of some local representations or descriptors. There's a lot of different choices and a lot of different neural network architectures. But in this particular one, which is a bit old-fashioned, but it's actually computational cheap, there are kind of 1 and 2 body terms. And so all of these parameters are what ends up being fit when you are basically developing your neural network. But the idea is that you kind of start with this neural network model, and then you kind of feed that neural network model DFT data. And then that DFT data kind of you kind of add more and more data until your model kind of is self-consistent and accurate enough. And in this case, what we've, this is kind of work a couple of years ago by Yusuf Shaidu. We sort of fed the neural network and trained it essentially on several different MOF structures, several different amine ligands, several different MOFs with the amines, with the CO2. And so there's sort of a training set that is developed here. And then there's a validation set, and these things are compared, and we basically kind of iterate until we feel like we have a high-quality network. And so for just to say, to train this, there were several tens of thousands of DFT calculations on large unit cell systems, and that's actually a lot of work. And so that kind of sets the stage for another topic, but which would be using foundation models as something to start with. But if you're not starting with that, there's still quite a lot of DFT calculations. And you may say, well, that seems like a lot. Couldn't you just do those, do 28K calculations and predict new materials? Well, it turns out that it's much more efficient to kind of feed this amount of data to your model and use that model, as I'll show in a minute. And so this is just some information about the quality of the model and different iterations in the active learning steps that we are. So one of the, how do we assess the quality? We just look at the difference in energy with respect to DFT and the forces. And so you can sort of see that after about 3 steps in this active learning loop, you get a pretty high quality model. This is another slide where I'm just sharing one more something under the hood, which is, there's a certain, you can ask how well does it do for the CO2 absorption energies. This is we didn't fit the absorption energies. We fit the total energies of a given configuration forces. So this is an interesting comparison. And so what you can sort of see is that the agreement is not perfect, but it's very good. And it can be about on par with the change in absorption energy when you use different exchange correlation functionals in DFT. Now, one of the things that we're using this potential for, and I'll just share one slide on that, is we are using it to do simulated annealing to kind of refine binding sites that we propose that might be relevant to comparing with experiment. We are also using it to study the first steps in CO2 insertion dynamics. So we're trying to understand that very first step where CO2 kind of displaces the amine, and we can do those kinds of molecular dynamics simulations with this machine learned potential. And then finally, we're using it to kind of explore different amines and how CO2 might bind to them. And one can do that much more efficiently with a neural network potential model. And so one of the things we wanted to just share with you is that we kind of looked at, so I mentioned before that these amine molecules are appended and grafted onto the interior of the pore. Usually it's a diamine, but these polyamines are also being studied. Here's an example of a triamine, and it turns out that if I introduce that into the pore, then there's a possibility of binding more than one CO2 per amine, and that would increase the amount of CO2 uptake. And so basically, to keep a long story short for the moment, we have a proposed kind of pore size that would accommodate and sort of binding mechanism for 2 CO2s per amine inside of this MOF, and so using this triamine. And so this is an example of a structure that has come out of one of our simulations that's being kind of worked on in Jeff Long's lab, kind of looking for that to make that. And the idea is that in addition to displacing the CO2, in addition to displacing the amine, it can also attack one of the other amines and then cooperatively hydrogen bond to an amine across the pore. So that kind of allows one to, and then you can kind of check how the energetics of these different amines look relative to, let's see if I can, relative to, you can kind of check the binding energies of the successive CO2 molecules, and they're all about the same, which sort of suggests that you might be able to load them off efficiently with multiple CO2s. So this is something we can check in the lab potentially, and getting into the space of now predicting materials that can undergo this CO2 adsorption. Now let me just say a couple more things about 2 other areas we were looking at, building these machine learning interatomic potentials that touch on optoelectronics. And so one is these multi-layer van der Waals heterostructures. So you're probably aware of 2D materials and graphene. And of course, in the last 10 years or 15, in addition to graphene, which is a metal or semi-metal, there are semiconducting 2D materials and insulating 2D materials. And one of the interesting things now is sort of stacking these materials and what new properties might emerge from stacking them. And then, of course, in the last 5 years, there's been not just stacking them, but twisting them. And this is a moire pattern that results from twisting 2 2D materials. And what you're seeing is the overlap of the atoms in the bottom plane and the top plane, and that kind of creates this pattern. And it turns out that that really can have a big impact on properties. And from these moire materials, one can see a lot of interesting condensed matter physics that may have some downstream applications in optoelectronics and catalysis and electronics in general. One of the things, just getting into it a little bit more, is that this is an example of an image of photoexcitations. This was taken at the Molecular Foundry, but this is a transition metal dichalcogenide bilayer, and these are images of excitons, or basically photoexcitations in the material, and you can see that they're spatially localized. And so there's opportunity to kind of shine light and spatially localize the perturbation of light on the material, and so there's some quantum applications of this. But what's interesting is that these are all basically in a regular array, kind of a lattice, what is called the moire superlattice, associated with potential minima that can be tracked back to this moire pattern that's connected to the twist. Now, that's been very exciting for a lot and inspired a lot of research. One thing that is a little bit kind of starting to be recognized is that when you twist these materials, they don't just, they're not rigidly 2-dimensional. They actually rumple. There's some buckling of the layers. And so this is a side view, and these are some STM experiments also from Berkeley where they measure how the height of the material is changing across the sample. And so this buckling is because as you twist, the atoms are kind of no longer stacked optimally, and sometimes they're too close, sometimes they're too far apart, and they just kind of relax away from one another. So one of the things that these neural network potentials can be very useful for is actually capturing this mechanical behavior. And part of the reason they're necessary is that when you twist, for example, as we've done here, two-dimensional materials, you are also expanding the periodic unit cell of these materials dramatically. And it can be hard, especially for arbitrary angles, to find a small unit cell that would be tractable to density functional theory. However, the machine-learned interatomic potentials can handle that because they scale better. And so this is work where, with Steve Louie's group, where we kind of were studying this. So Steve has been studying these Moiré superlattice for quite some time. And so here in this, we're using the same neural network potential, but adding a term that accounts for the non-bonding interaction between the two layers. This additional local representation we thought would be more efficient than the standard neural network potential for this class of systems. And basically, the other thing I should mention is that all of this neural network potential was trained using only very small unit cell systems. So that's also an efficiency gain. And the way we do that is we use metadynamics to do finite temperature MD and explore all possible stacking configurations in a very small cell. And so maybe just to kind of get to the punchline of this work, in the interest of time, here is some work where here's another experiment, not in Berkeley, where they measured corrugation of MOS2 bilayers on top of HBN substrate. And here is the experiment, and here is the theory. And in particular, along a similar cut, we can kind of compare the two curves. And one of the nice findings is that if we look at a bilayer curve that is not supported, just suspended, no substrate, we see higher amplitude rumpling, if you like, than the experiment. But if we add the HBN substrate, we recover the experimental amplitude of the rumpling. So this is a very large unit cell that would be kind of difficult to study with standard density functional theory, but it becomes possible to study with neural network potentials. And I think this kind of lays the groundwork for us to now start looking at electronic properties with relaxed structures, capturing all the corrugation, et cetera, using with high accuracy. And I did want to mention one other thing is that we can compare our approach, which is a little bit computationally cheaper than sort of the foundation models that are out there. And it compares very, very well in terms of the energy and also force metrics. And I think if I have just a couple last minutes, I can just say one other thing, and I can wrap up. But basically, the last topic is sort of looking at organic semiconductors, and they have interesting energy implications because they can undergo singlet fission, which is a process by which a single photon can generate multiple carriers, so they can be advantageous for solar applications and LEDs. And there's also been some interesting carrier transport behavior that's been recently reported in them. These are systems for which the molecules are kind of packed in a herringbone way, non-bonding, but and so you might expect carrier transport to be weaker than in a conventional semiconductor, but it's been reported that the carrier transport in these systems can be enhanced as a function of temperature, where you might have more dynamical disorder, and that's kind of interesting and not understood. And so using a neural network potential model for the molecular crystals, what we were able to do is, and some work that the rest of my group is doing that's focused on excited states, we were able to kind of take a thermal average of the excited state energy of the lowest exciton or photoexcitation, and that thermal average was enabled by a machine learning potential, kind of looking at snapshots of trajectories that includes also quantum effects. And basically what we were able to do is show that indeed that if although within the harmonic approximation the average size of an excitation increases with temperature, which is kind of consistent with that measurement. If you add anharmonicity, that introduces additional restoring forces that actually reduce the size of the excitation and suggests that for at least pentacene, there would be no such carrier-induced delocalization as a function of temperature. However, we have identified kind of a way that you might be able to do that through if you could remove this anharmonic barrier. And so that's kind of a value of this sort of simulation. So this is an example of studying, excited states with these machine learning potentials that might be, kind of something we will do more and more in the future. And so just to kind of close, I talked about a few different examples at a high level. Look forward to your questions, where we're developing platforms to study systems with greater structural complexity and look at their properties and assess them for different technologies potentially. And furthermore, maybe just to say, I think these tools that are surrogate models for DFT, I think they're very powerful. And they're particularly bringing us into the finite temperature and dynamical realm with DFT accuracy. And I think there are many opportunities in studying elements of materials that are non-bulk and non-crystalline that could have real relevance to energy technologies. So I think with that, I'll leave it there. Yeah.
Okay, so as I mentioned, we will hold questions till we get to the panel part, and so I'm going to now introduce the next speaker, who is Maria Chan. We thank Maria for traveling out here from Chicagoland area. So Maria is a scientist at the Center for Nanoscale Materials at Argonne National Lab. She specializes in AI and ML-driven material science for renewable energy technologies, and really has worked on a broad array of applications: solar cells, batteries, thermoelectrics, and catalysts. Maria, you will see, is not only an expert in sort of the computational techniques, but also in analyzing experimental data. So we may see some of that in her work, in her talk. For all the work that she's doing in the community and her contributions, she's been named the 2024 Fellow of the American Physical Society, and she also received the 2020 Department of Energy Early Career Award. So please join me in welcoming Maria, and we look forward to your talk.
Thank you so much. Can you hear me? All right. So thanks for the introduction. Thanks for organizing, Christian and Sarah. And it's very difficult to follow Jeff Neaton, not the least because I have burning questions about the work he was talking about. But I will try. So my talk will be on, like Mark said, more focus on how we are understanding the materials from a combination experiment and AI. But before I get to that, just in case, I wasn't sure if I was going to go first. I just wanted, and I was told there was going to be a board audience. I just wanted to start with, connecting climate and energy to materials. Maybe I don't need to do that. So one piece of good news, this particular image was downloaded this morning on NOAA's website. No, last night on NOAA's website, and the title was like the effect of climate change. So that hasn't disappeared completely. And then there is climate is intimately related to energy. There's a little bit of capture, but most of it is really energy. Energy capture, storage, conversion, and conservation. I was just curious to follow, all the energy usage trend. The fact that you can see solar is really remarkable. This was not actually conceivable 15, 20 years ago. And energy, it's intimately related to materials. I was trying to list all the different ways that materials are related to energy capture, storage, conversion, and conservation. And I was listing all the different types of, areas of research for those energy. And I came down to conservation, and then I actually wrote lighting, and then I decided to make that gray, because that is probably one of the few things that are more or less solved. I don't know if people disagree, but lighting is just dramatically changed. in terms of energy usage. But now, of course, our big problems is electronics, all the data centers, the use of AI. I was told yesterday that saying thank you to ChatGPT costs millions of dollars, and I presume generate a lot of CO2. So in conversion, we talk about thermoelectrics, but also catalyst is a very important area because 30 to 40% of energy use actually has to do with industry, and a lot of it based on chemical reactions in industry. So having more efficient catalysts, not just for solar fuels or CO2 or whatever reduction, but for all the chemical processes in industry, that is actually very important. With all of that, we need materials, functional materials. Some of them involve structural materials, also related to, say, building insulation and so on, and we're not going to talk about that. But functional materials basically dominate all of these energy materials needs. And for functional materials, what we care about are their functional properties. For solar cells, how much they convert sunlight into electricity. For energy storage or hydrogen storage material, how much they can store. For catalysts, the activity and selectivity. Thermoelectrics, how well they can generate heat from electricity or vice versa. And then for electronics, performance per watt, how much compute you get out of every bit of energy you put in. So functional properties, most of you know, but some may not, depends on two things: chemical compositions, which element in the periodic table you put in, and also the structure. I think structure is it's a word that carries a lot. People think of structure as a crystallographic structure. I think we can thank the protein people for that. You think that once you take an X-ray diffraction, you solve the structure and that is it. It's not really the case for materials, because materials inherently have many different length scales, unlike proteins or maybe drug molecules. So there is a lot of structure in the nanoscale. So we're not just interested in a piece of crystal and the space group and you solve the crystal structure. We're interested in things like interfaces and surfaces and nanoparticles, nanotubes, combinations of nanoparticles and 2D materials, such as the example here. This is a work we did on a catalyst that was a nanoparticle combined with a nano-structured graphene 2D-like material with some metal centers. So nanoscale structure is actually what drives a lot of these functional properties. So, of course, Jeff already talked about how density functional theory has really made a huge breakthrough in terms of being able to study materials computationally. I was interested in trying to explain to people who don't work in density functional theory how big, how significant density functional theory is. So I searched on Google Scholar with quotes, density functional theory. That is slightly cheating because there is actually nuclear density functional theory, which is not the same as electronic density functional theory. However, they are very, very small, pun not intended. So there's 2.3 million. This is probably a month or two old by now. 2.3 million papers on Google Scholar on density functional theory. How big is that? So the only other reference point I was trying to make was X-ray diffraction, because that sort of rolls off the tongue all the time. So I looked up X-ray diffraction. Anyone want to hazard a guess how many papers on Google Scholar have the quoted word X-ray diffraction? 4 million. Okay, so 4 million. So DFT is almost at the level of XRD, but XRD is 100 years old. I won't say a million, but no, 100 years old. Okay, so that's sort of the monumental. But we are replacing it. You saw, Jeff made his career doing DFT and related calculations, and now he just throws it away, right? He does, use machine learning. And this is not, this is not a small thing. Oh, there was one more point I was trying to make. DFT has enabled all of these huge materials database, including the Materials Project, one of which was the first and biggest, but also Open Catalyst project from Meta, for example, which is a rare form in industry for open database. Even in other countries, not just the US view, in Europe, there's Nomad, which is also a very big database. So DFT enables big data for materials, but now we don't want DFT anymore because it's slow. So I would say that, 8 to 10 years ago, we have these pioneering papers. I guess that's only 7, but anyway. Now they're cited several thousand times. And then some of the other papers have like mind-boggling impact. The Google paper was accessed, 250,000 times for scientific research. This seems huge. So today you heard, and tomorrow you hear more about how all of these graph neural networks, machine learning potentials have revolutionized how you can predict properties from structure. And this is really an amazing capability now that we can do that. Either dynamics or static or even electronic properties can be derived from structural information. What I am interested in is how do we get the structure? Because you always have to start with a structure. It doesn't matter how powerful your foundation model is, you always have to start with a structure in order to get a property. And getting a structure, as I said, is not easy, especially in the nanoscale. Just using an energetic information is not enough. This is an example using density functional theory, relatively accurate form of it. And this is a system just very simple, like 14 gold atoms. What is the arrangement of 14 gold atoms that give you the lowest energy? Turns out it's flat, which is very strange. It's like a little piece of paper. But there are many other structures. Some of them half flat, half 3D. Some of them is a very nice pyramid. All of these structures are within a very, very small energy window of the lowest energy. That means just theoretical considerations, no matter how good your DFT or derived machine learning potential is not enough. And this is just a very small tip of the iceberg. In general, because of the low symmetry for nanoscale structures, there's just too many near degenerate, so meaning very similar in energy structures, for a pure computational approach to work. Which is why we have been really focusing on using a combination of all possible information, that's why I put in the kitchen sink there, to get at the structure, find out. So I work at Argonne National Lab, one of the DOE lab, just like Berkeley Lab. And we have this huge synchrotron. There's a baby one up the hill here. No offense. The synchrotrons are very powerful X-ray machines. They look into the structure of materials. We also have, as many institutions, electron microscopes, atom probe, and they generate a dazzling array of data. There's one-dimensional data all the way to 5D data. Some of them are small, kilobytes, some of them are terabytes an hour. So there's a lot of this data, and our goal is to figure out how we can use a combination of anything we can get our hands on, which includes AI/ML, to find the atomic structure, the nanoscale structure from this data. So we call our whole group now Material Eyes to see the materials, but also materialize, make things happen. Can we see all the atoms in 3D? I know atom probe people will tell you that they can, but they actually obliterate the whole thing and try to reconstruct, the model. We can argue about that. Can we see the oxidation state? Can we see a defect in an interface? So in order to be able to do that, we need first to be able to fool the experimentalist. We call that forward simulations. If I take atomic structure and I simulate a measurement, can I make it high fidelity enough that the experimentalist will not question it, or computer code can recognize it as similar? This is what a lot of our work has gone into. Some of them involves physics-based learning, simulations. Some of them involved really understanding and controlling noise, because a lot of times simulated data is too clean and we need to put in the right noise. And sometimes improving the speed of these forward simulations using neural network models. So that's part of it. It's critical because if we cannot produce a spectrum or a micrograph or some kind of signal that can be measured. We would never know if we got the right answer. We would never know whether the structure that we determined to be true was actually there. So this is the key. We've also used some more traditional computer vision approaches to do automated matching. How do we know this match between forward simulations and experimental measurement is right? For some simple things like 1D spectrum, it's already not trivial. There's a lot of interesting story about metrics comparing two curves even, but when it comes to two images or even higher dimensional data, the matching has to be done automatically. And once we have those two ingredients, then we can sort of go to town. We can work on some pre-trained models that extract a piece of structural information from the experimental data. This is an example for, can I click on this? It's not playing. There we go. For 4D-SEM, this is actually work done in collaboration with Berkeley Lab here. Kolonofis, he abandoned us. 4D-SEM is two-dimensional plus two-dimensional. So the electron beam goes around in a 2D array. And then each point gives you a two-dimensional diffraction pattern-like data called CBET, convergent beam electron diffraction. It's not quite the same because there is multiple scattering. The electron beam interacts much more strongly with the material than an X-ray beam, so it has the effect of basically messing up the diffraction pattern, giving disks instead. Our goal is to extract the actual diffraction pattern, the disk, so that we can get things like crystal structure, orientation, and strain. So, this seems like a straightforward problem. You can have pairs of the CBETs and Brecht dispositions, and then, you can train a convolutional neural network. We were still doing that then, to go from this to that. If you were to try to do that experimentally, it would be impossible. There's no way to actually have the amount and fidelity of the data, because if you pick up a piece of material, you don't necessarily know what's the strain and crystal orientation. So this is where simulations and modeling come in, and this is why I live in this strange world of everything in a bucket. My simulation background taught me that I needed to sample the different crystal structure prototypes in the materials project database. Actually, there was another AFlow lib database that provided the prototypes. I needed to sample all the different chemistry, atomic weights, and so on. So that provided us with the training data of about 200,000 pattern to pattern, which would have not been possible. So that's why I'm arguing, if you sort of take one thing, is that I think it is really important for us to all to work together, simulations, experiments, AI, ML, to get this problem solved. So we train a neural network model. The only thing sort of novel about this is that considering that we are looking at a reciprocal space object, for the mathematicians, you can wake up a little, we were interested in how to relate the crystal symmetry and structure, which is in real space. So we took a Fourier transform of the CBET pattern. We fed both into a neural network and kept complex weight. Now, I can't prove it mathematically, but that actually turned out to have much better results. Here are a couple examples. This is the data you get. These dots are what you want. You can see that for a clean one like this, you can use a conventional method and get reasonably good results. And the neural network gets slightly better. But for something messy like this happens when you have a thick enough sample. You can't tell those dots apart at all, those disks apart, but the neural network still does a decent job. So that allows us, when applied to experimental data, to determine things like strain, which is how much the crystal has expanded or contracted, with higher accuracy, and more importantly, much more automated way, reducing the amount of time it takes. Because as you'll hear a lot from the next few speakers, automation is going to be very important, and any automated experimentation should be coupled with automated data analysis. Another example of a pre-trained model has to do with representation. So for those who work in AI, I think it's sort of an understood thing. When I learned about it, it was kind of very interesting because I had, it was a new way to think about it. So the data here, for example, is what's called core level spectrum. When you excite an electron from the core level to the valence level, it tells you something that the absorption spectrum as a function of energy tells you something about the local bonding. That absorbing atom, how is it bonded with the nearby atoms, how far apart they are. So core level spectra is a very useful tool for us to study material structure. The question is, you have a 1D vector, 100 to 300 elements. How do you represent it? What is a good way to actually use it in machine learning? So there's a lot of things floating around. Everyone loves variational autoencoders. We kind of use it too. But we were wondering, is that the answer? Why is that the answer? So we went and did a sort of systematic study of the different representations. So we can take the vector by itself. We can actually integrate the vector, which is called cumulative distribution function. I resisted that suggestion by my collaborator, Mike Davis, at first because I felt like they were the same thing. He had to throw a lot of books at me on measure theory and whatnot, and I accepted. And that was a good thing because that turns out to be very useful. We looked at the peak representation. You have a curve. Humans look for the peaks. So can I just decompose them into a bunch of peaks? That's a way to represent. So with all of these different representation, we wanted to see which works better for machine learning to extract information. The data we use, again, you cannot collect enough experimental data for this whole scheme to work ever. We have 3,000 core level spectra, usually in 7 days of a synchrotron run. A synchrotron is a multi-billion-dollar machine. You are lucky to get 20, 30 spectra. We have 2,800 spectra, and more importantly than the number, we have the ground truth for these spectra. We know exactly how all the atoms are arranged, which you cannot say for any experimental data. This was for a battery situation. This is the battery that's probably in most advanced applications, nickel, manganese, cobalt, oxygen. And we have different amount of oxygen, different amount of the transition metals, and different mixtures. Okay, so the results are here. It's a lot. Every row is a different way you represent. Every column is a different machine learning model. These are small, so they're not going to be neural network type models. They are gradient boost, random forest, multi-layer perceptron, small machine learning models. Light colors means better. So you can see several of the yellows over it. These two columns work better, several rows work better. This is for oxidation state, to know if the nickel is 3+ or 4+ charged. This is for bond length, the distance between the nickel and the nearest oxygen. Similar story, a lot of yellows. If I wrote a paper here, I would say, okay, actually you can featureize it several different ways and you can use several machine learning models and the results will be pretty good. But if I wrote a paper there like that, that would be irresponsible because we have not used the machine learning models on realistic data, which means experimental data. We did actually ask for experimental data, only 8 of them, that's all they could muster up. We apply these towards the model. The blue is the voltage. The green here is the oxidation state. There are 4 different lines from 4 of the different featureization. And you can see that, so for those who don't work in batteries, when you increase the voltage, you expect the transition metal to be more oxidized, charged, more positive. So the voltage curve should follow with the oxidation state curve. And you can see that only one of them does that. All the others don't. And that's the CDF. That is the one I was going to throw away because it's just a simple integral of the spectrum. Somehow a representation that's not that different actually gives you much better accuracy. That's not a fluke. For nickel oxygen bond length as well, that's also the case. And in this case, we actually have ground truth. And we wanted to go beyond that. This was one metal, one edge. It gives you something that is sort of a bulk average. We wanted to see if we can use this approach to see individual defects or at least defects in a small volume. So that's possible with electron spectroscopy, EELS, electron energy loss spectroscopy, where you can see simultaneously the excitation from oxygen and from the transition metals. Those are different edges, we call them. We find that using the same approach, simulate structures with some defects, take the spectrum, and then use machine learning to determine if you can tell that there was an oxygen vacancy, if you can tell that there was an anti-site, the lithium and the transition metals are switched. So it turns out very interesting, maybe not surprisingly. The approach that uses all of the edges work a lot better, a bit better here and a lot better in the next, than any individual. And interestingly enough, to tell whether an oxygen vacancy is there, the oxygen actually gives more information, which is weird because the oxygen is further away from the metal. This is the anti-site, another type of defect, combining different data stream. So again, these are all simulated. I didn't want to be irresponsible, but now it's much harder because we don't actually have an alternative way to tell if there's a defect at an interface. This is sort of the double bind we find ourselves in. If there was an alternative method, we would not need this, okay? But if there is no alternative method, how do we know we did the right thing? So we have some more sort of, 2 or 3 step logic data from our collaborator, Miao Feng Qi. Essentially, they measure a sample with some silicon doped in. And there have been discussions and evidence that silicon promotes oxygen vacancy formation. And we find that using our machine learning model, we also found that where the silicon atoms are, it's much more likely for there to be an oxygen vacancy as inferred by the spectra. So that's the corroboration we have at this stage. Of course, we're looking for more. All right, so for the final few steps, pre-trained models are great if you know or can reasonably enumerate the possibilities. This is not always the case. When it comes to figuring out even just 30 atoms, where to put them in a box, it's impossible to enumerate. So there's a lot of generative methods that are needed. Generative sounds like a new word, but it's not. I mean, for many years, computational modelers have been trying to create different structures in many different ways, statistical and physics-driven and everything. So our approach for generative structure determination really combines all of that, making new structure plus corroborating the energetic information with experimental information. We want to know where the atoms are in the realistic sample, not in theory, not by fitting, but both. So Fantastics, which stands for Fully Automated Nanoscale to Atomistic Structure from Theory and Experiment, really just takes a simple idea of combining different pieces of evidence. Can we match the experiment? This is called fitting in the experimental world, and it's 60 years old maybe. Fitting is not enough because fitting sometimes give you non-physical structures. The other side is energetic simulations. Simulations alone is not enough because there's a lot of degeneracies. But if you combine the two, you have a much better chance of getting at what's real and what's physically realistic. So this is an example of Fantastics in action for electron microscopy image. We started with the simplest way. This is an experimental image. It already gives you the 2-dimensional projection of the atomic structure. And we're trying to create the 3rd dimension, essentially. So Fantastics basically goes around and search all the possibilities, especially at this interface where things are a lot messier, and then simulate the image. We got to match the image. We got to have a low energy. So that gives you a structure. The key here is that, or actually a family of structures on the Pareto front. The key here is that these structures are realistic and they are messy. Modelers don't like messy things. They are not something that I would come up with on my own or anyone who do modeling. Even for clean structures, this approach reduces time. This was actually a work that we did before we started Fantastics, where we had to find out what this snake-like structure was. And then, it has to match with the rest of the crystal. And it took a few weeks, maybe a month or two, waiting and iterating and really staring at the computer and moving atoms by hand. But with Fantastics, it took like 2 or 3 days, most of that waiting on the queue. So with Fantastics, we now tackle a lot of different experimental data, X-ray data. Did I skip that? Okay. X-ray, different types of X-ray data, scanning probe data, and so on. And just want to reiterate, for those who do modeling, it's clear why we need the structure. We need the structure to get the property. But for those who don't, it's sort of necessary in the sense that if you want to explain something about your material. For example, this was a case in a Nature Energy paper a couple of years ago where we looked at how batteries fail. And batteries fail, same material, sort of slightly different microstructures, they fail at different rates. Why is that? So you could, start by creating a library of interfaces in these materials. It was found that the density of the boundaries mattered. But instead, we went and looked at the experimentally observed interfaces and did modeling on that. That makes the results much more relevant. And other reason we do that is to do materials design. If I know the structure of a defect or dislocation core, I can figure out how to mitigate it. So that was the case for photovoltaics, cadmium telluride solar cells. We actually did simulations to figure out what would passivate some of the realistically observed grain boundaries. And actually, palladium was one of the answers, except that First Solar already knew that 3 years ago and they didn't publish it. So, that's life. The other reason we want to structure all this whole workflow is to accelerate all this in situ data processing with all these upgrades of synchrotrons and other machines. Data comes at you fast, you need to analyze it fast. So last minute, I want to talk about data. If Christine was here, she would murder me because data is much more important than the last minute. But the key among all of these work is that I need the data, the experimental data in particular. We saw that there are millions and millions of computational data that is, you can just easily get on your phone, in your shower, anywhere. But experimental data is so much harder. So we want to first, and this work here at the Molecular Foundry by Ed Bernard, it's very important to build up a data infrastructure to capture data as it is being produced, and have the proper metadata. So actually metadata is very important. The other thing that we're doing kind of, not in a intellectually satisfactory way, but in a practical way, is collecting these microscopy and spectroscopy data from literature. So it's really cool that now LLMs does everything so well. We actually started too early, and we had to struggle with Spacey, and that was so painful because Spacey didn't work at all. So one of the tasks we were trying to do is to separate a caption into different parts of the text. Okay, all right, I'm scared. Okay, once we have extracted the data, we can do a lot of really cool AI with it. We also digitize the spectrum. I will just, this is my last actual slide. An example of how we use this is to drive the autonomous laboratories. We can extract literature data about molecules, digitize the optical absorption spectrum, and then train models. And this was applied towards developing electrochromic polymers, so color-changing polymers. I'll skip over some of this. So our GitHub is called Materialize, as the name of the project. And just to summarize here, I will actually thank my collaborators' funding, and we are in a user facilities, and I'll take questions later. Thank you so much.
That's okay. Thank you, Maria. Great talk. Okay, so we'll move on to the third talk of the session, which will then again be followed by a panel after that. So I'm going to design. So let's welcome Gabe, and we look forward to his talk.
So, can I use one of those?
Sure, you can walk around and do it.
Hello? Okay, all right. Thanks for having me. It's an honor really to be here. There are many heroes of mine in this room. I don't know what I'm doing here, but I'll try to tell you a little bit about our work, which is pretty different from what the previous two amazing speakers told us about. And yeah, so I'm an assistant professor at Carnegie Mellon. I started there in 2022, departments of chemistry, chemical engineering, and also in department of machine learning now. And this is the most important slide, right? The people that are doing the work here. And today I will be telling you mostly about the work from Daniel Boyko and Rupert McKnight in my group, which is on this idea of how we are trying to get to the next step in this new science that we are all inventing together. My group has been working on this idea of reaction discovery optimization in the age of digital chemistry. And we want to go from the idea of automated computational models and more autonomous to autonomous chemical synthesis. And I put a star in synthesis here because that means characterization as well. If you don't characterize, did you make it? I would say probably not. But we are interested in that. And we merge machine learning, computer science, and automated synthesis with fundamentals from physical organic chemistry and catalysis to develop new materials. We have been on this bit for a while now, and some of the papers here that really solidify the field that we're trying, or at least our contributions to the field. And I'll tell you a little bit about some of these works today. My group has been really interested in going from the fundamentals all the way to devices and things that would be useful for people. And here's an example from when I was a student, a collaboration we had with folks at IBM, down the street, I guess, from here, where using computational methods, we were able to design this organocatalyst that accelerated these polymerizations quite a bit. And then these fluoropolymers can be used for medical devices. But the reality why we want to do this is, of course, the reason why we are here today. And we need to take action to stop climate change. And even if you don't live in a beautiful place like Berkeley or San Francisco or here in the Bay, I do live in a beautiful place called Pittsburgh, you still have the river. And even then, you do not want your cities to turn into ovens, which is happening. And we must take action to prevent the worst of climate catastrophe, right? But if you're cynical and you just say, you know what, forget about it, I just want to make money, that's fine. Barron's in 2019 had this really interesting article saying the 3 technologies that could create trillion-dollar markets over the next decade. The first one was post-digital computing, where quantum computers and noiseless quantum computers, more recently thermodynamic computers and molecular computing, have been playing more and more of a role. The second one was prescient, and it was for CRISPR, and of course, I got the Nobel Prize to Jennifer Doudna here at Berkeley, and Amela Chapartier. And the third is where I think we can do something about, which is material science, which I can say it's everything. Materials, drugs, energy, transistor, devices, you name it, those really fall under the umbrella of material sciences. It takes about 10 years and over $10 million to make a new material, give or take. But the question that comes is, how do we make materials? And I put a star there because I'm actually a chemist by training. So my question really is, how do we make molecules? And it turns out that for about 35 years now or more, we have been worshiping at the altar here of Silicon Valley of bits. But reality is that scientists have been designing and developing and controlling something quite a bit more difficult, which are atoms with catalysis. And of all industrial processes, 85% are catalytic. But when you go to catalytic processes, only about 20% fall on the umbrella of bio and homogeneous, which is where my group focuses our attention. And there's a conundrum for us to solve, which is by 2050, there's a projected increase in demand of our industry of 180%. And at the same time, we need to have at least a 30% reduction of absolute CO2 emissions by the industry. And this is important because our industry accounts for 7% of all greenhouse gas emissions. So, what do we need? Better catalysts for better industrial designs and processes. But from the concept to the discovery and development can take years. I will say, and I don't think this will be controversial in this audience, the computation, AI, and automation are helping us accelerate these timelines, but not fast enough. Just not fast enough. And my group has been working on a few of those things. And when it comes to AI, one of them is try to solve the difficulties that come for biocatalysis. So this work here, and you can scan this QR code to go to CatNip, is a tool that we developed in collaboration with the Narayan Group at University of Michigan under the NSF Center for Chemoenzymatic Synthesis, is something that kind of tries to tackle a holy grail. Because enzymes are great. They're very specific, specialized machines. Here are some examples of total synthesis that have been developed and are even on products that you can buy by pharma, that you have specificity, selectivity, and sustainability, but it's very hard to predict. Enzymes are very, very finicky. So if you think about how everyone that has been working on this, you either have one enzyme that you know about and search for some substrates around the local chemical space, or you have one substrate that you know about and search for a local sequence space. We thought, well, why not por qué no los dos? And join them in a joint space, chemical and sequence space. I'm not going to tell you the details here, but if you like Netflix, if you like catalysts, this is what CatNip looks like. So you can go and you can select the substrate of your choice, and it will first place it in the chemical space of this family of enzymes that we have here, which are iron-dependent non-heme alpha-ketoglucerases. And it will place in the chemical space that we had for these reactions. We end up discovering 215 new transformations. And then it will rank them. I had the luck to have a student in my group that worked with search and recommendation systems before coming to do his PhD. And you can see the molecule that I drew there in the chemical space. Things that are close look like it, things that are far don't. And you can then, get the sequence here with 54% chance-ish, 55, that you would perform a transformation on that substrate. But let's refocus. So today I'll tell you, focus on co-scientists. The OG one, not the Google one. And we can say that almost every technology that humanity created followed this path, where someone thinks about it and makes and tests and analyzes. But not much has changed over the last 100 years in what a lab looks like. Maybe now there are more people that look like me, and that's a great thing, but that's not enough, especially if you look at all other offices and where people do work. Some of us have been thinking about this idea of self-driving labs for a while now, and the design is managed between human and machines, and robots can make and test, and analysis can be in this closed-loop fashion in a reinforcement or active learning way. But this is not straightforward. If you've ever done any experiments, you know that there are many complex variables that go into it. And here are some of the ways that you can think about doing this, but reality is this is not straightforward. It's not impossible, though. Some of us have been able to do that, and some areas we got a little faster. Here's an example of a collaboration we had with Mark a few years back, where we use a Bayesian optimizer to control this cam speed robot to optimize a pretty complex Suzuki reaction. This is great. It's less labor intensive, but still requires experiments to be designed by humans. And that's challenging. Because this is the question that has been in my mind the whole time. How can I make this faster? How can I make this easier? How can I make this more accessible? Ideally, what you have is something that only requires a natural language prompt, and it's a seamlessly integrated with an experimental automation. And I like to think about this as the idea of crunching bits, where you give information, prompt in natural language, into atoms where experiments are realized in the physical world. And that's what we had first as a preprint in April 2023. This was less than a month after GPT-4 came out. And later on, a paper in Nature in December that year. And that paper introduces co-scientist, which is this system that we have. If you see something in red, that comes from a human scientist. If you see in green, it comes from co-scientist. Co-scientist then, that's not true anymore, was composed by a planner, a web searcher, and a documentation searcher, all three of those modules powered by large language models, and a few other modules that are not. For example, a Docker container for code execution for safety, and possibility of performing experiments via automation that can be done in a cloud lab, with robots in my lab that are liquid handlers, or by protein-based robots, also known as, well, trainees, I guess. I shouldn't say that. Anyway, so, and we validated our system with a series of tasks that are very common for a lab doing any scientific research, but specifically for chemistry, including performing some reactions. So the way this works is actually that simple. If you start with something like synthesize ibuprofen, initialize a task with the planner will do what most of us would do, which is search Google, and ask the web searcher to do that. And then the web searcher comes back with some definitions. You need to do a Friedel-Crafts tessellation of acetylbutylbenzene and acetic anhydride conditions, stoichiometry, etc. Planner is not satisfied with that, so ask for more information from the searcher, which then retrieves that. And you can keep going. And one of the most important things here that as scientists we worry about is, well, if I'm using something that's probabilistic, like a language model, hallucinations could be very, very dangerous. We tackle this by grounding co-scientists with documentation, in this case about the hardware that we have in hand, but also could be with any documentation that you have, papers and so on. So let's do some experiments. The first thing we did was with our robot, it's an OpenTransOT2, open hardware, open software. We gave a plate with food coloring and just said, draw something cute on this other plate. And for whatever reason that we still don't know, and better not ask, it drew a fish, which is nice, but this is only one thing. You can now talk to hardware in plain English, and that's what we show here. You can control these robots in very low-level instructions. You can say, draw a red cross, use food coloring, or color every other row, or draw a blue diagonal, etc. Okay, fine. But we are chemists, and until I see bonds being broken and made, I'm not satisfied. So here's what we did. We asked for it to perform Suzuki signature reactions to find the appropriate reaction first, and only then perform the experiments. And we give a description in plain English of the setup, which is to say, on this well you have this alkyne, on this well you have this boronic acid, and this arrow halide, and so on. And if you know anything about organic chemistry, you know that these reactions are very similar, but they are not the same. So it had to figure out how to do that. And what I'm going to show here real quick is a comparison On the left is a brilliant student of the group, Jose, and on the right, Jose gave me permission to show this. On the right is co-scientist, and I'm showing you a different, just a different way of seeing it. But in 6 minutes, co-scientist was able to write the code to perform those reactions 5 times over. And on the left, unfortunately, after 15 minutes, the code that Jose wrote wouldn't even run. But if you take any of the codes that co-scientists wrote and you do run it, this is what you see. And it doesn't look like much, right? It's just hitting and shaking in this 96 well. But what you see on the left is quite striking. We have here a chromatogram and mass spec for these reactions. And you know, we got about 55% yield for these reactions, which is not great. These reactions usually get much higher yield, especially for the substrates that we chose. One of the reviewers complained about that. But if I were to do something for the very first time in my life, and I got 55% yield, not bad. But more importantly, and this is what spooked me, when I saw this, I saw that for the very first time, a non-organic intelligence, however you wanted to define that, planned, designed, and executed complex scientific experiments that have been developed by brilliant humans that worked a lot on this. That's just remarkable. And what we see here is that you can go from an English prompt to this complex, fully realized complex scientific experiments. I'm not going to tell you about all the risks and dangers about this. We can talk about that. But I want to tell you what comes after you have these kinds of superpowers. So we're leveraging co-scientists now for the next generation of automated experiments, especially in chemistry. And we use co-scientists to help us design this process with the hardware that we have. So we have in this case, we had, at that time, 2 robots. We have 4 now, and UPLC QTOF. And what we did is we used it to help us design a way that we can do extreme scaling of chemical reactions, data set generations. The reason for that is, well, it's boring, but it's simple. If you think about how much it costs per one data point for images or text, and you compare against one data point of a scientific experiment where you have full provenance and understand everything that happened there, it's not even on the same scale, right? And what we want is to be able to make those data points much more accessible so that we can have the best kind of models possible going forward. So that's what we did here. And we use a very simple reaction to telescope this. I'm not going to bother you with that. Co-scientists help us figure out how to make our very cheap robot be able to do that. And we're going to have this out soon. But what is most interesting is that we're able to have over 1.2 million compounds characterized with kinetics, which is something that usually you don't see people doing for these kinds of scale for experimental work. So one of the questions throughout this process that we got the most was, how can you leverage previously collected knowledge? Maybe it's in your lab, maybe it's in your company, doesn't matter. And that's a great question. We decided to frame that as a reinforcement learning game or just an optimization problem. And I'm skipping a few steps here, but here's what I want you to notice. For this particular reaction, there are 5,500 possibilities. And the goal is to maximize the yield. And we rewrite the yield as this metric, normalized advantage. The point is, follow the black line here. Co-scientist in this case has only 20 iterations to do this. And what you want is to get as close to 1 as possible. At that point in time, if you gave GPT-4 10 randomized points to start from this reaction, you start a little bit better than random, and then it keeps growing, and it gets to pretty good conditions. If you do not give any information, in-context learning back then was quite powerful and allow you to get to, at the limit, get to the same normalized maximum advantage in about 19 iterations. That is great, because now I know that if I do not have much data to start with, I can get to a point, if there's enough information about that process, that it will be pretty good. And we decided to think more about this. My group had been working a lot on Bayesian optimization, and while Bayesian optimization is quite powerful, one of the downsides is that if you don't have enough understanding of what the process is, you don't have interpretability. So in our case, coscientist not only performs at the same level or better than Bayesian optimizers that we incorporated mechanistic information, but it gives you the reason why. So in this case here, in the middle of this optimization, this is a different data set, just 4,400 possibilities, but still, the yield has improved very significantly. Let's try the first ligand again and change the additive. So this is the additive, and you observe that the yield of this reaction is 41%. Okay, the yield has improved to 41%. Let's try another additive that has a strong electron withdrawing group to further increase the yield. It's very much how a medicinal chemist would talk about this. And indeed, it gets a yield of 50%. And it keeps doing that until it gets either uses the budget of experiment or gets that maximum. So let me close this loop. Because of we noticed this, we decided to build something, a tool, and also a benchmark. One of the main difficulties right now for understanding foundation models is that, well, you can kind of come up with things that get hacked for growth. So we started this project, which I have no idea why our collaborators at FRL and my student decided to call the Iron Mind. I think they were trying to make some analogy to Iron Man. I don't know. Don't quote me on it. Well, you can quote me on it. But the point is this. It's humans versus AI. So humans, like really, really knowledgeable folks that have been working on a problem for a long time will still beat a lot of these problems. And the way we did this is simple. If you're a human, you select the data set that you want to work on, you set the campaign parameters, and you're going to run this optimizer. We try to make this very nice for people to use. So here's that data set again I talked about earlier. Everything you see in blue is a variable. And the thing here is, I give you a chance of understanding how difficult this problem is. You want to maximize the yield. And here's the distribution of yields for this reaction. You see that most of them are around 20%. So this is going to be tricky, but it's possible. So as a human, you go in and you choose. You can see your molecules in 2D or 3D. And then after you select all the variables, there's a space for you to enter. Why did you choose that? The ML people probably already think, oh, okay, you want to do some reinforcement learning. And yes, we do. And we compare that against Bayesian optimization, which, well, you're not going to have a reasoning. And finally, our LLM optimizers, which is going to work very much like a human. In this case, the LLM has tools to select experiments from this defined parameter space, and that really helps. And we have it writing why it chose what it chose and give an explanation for that. For each batch, the model needs to provide that reasoning for it. And here's what happens. In this case, this is back in the very end of 2024. We see the top performers being O1 and Claude 3.5 Sonnet. This other case, once again, Claude 3.5 Sonnet. And this other case is O3 Mini. And if you keep looking at all the data sets that we have, you see that emerging. We have a past set, many iterations, and you see that Sometimes you have the Bayesian optimization coming close. Sometimes it's even in the top 3, but it's never the top 1. I really want to emphasize that. So if you'd like to help us make this better, you can sign up for a public launch. Just scan this QR code. I hope it's working. But last thing I'll tell you is about what comes beyond co-scientists. And the premise of co-scientists that I told you earlier was to go from this prompt in natural language bits to atoms. And if I put as a graph, it's a directly cyclic graph that you have your initial point and your objective. We don't think that that's where it should end. And as scientists, if you in the middle of a research quest, you will find yourself in problematic situations. Things do not work. Adapting is critical, and self-healing is critical. So we are developing an operational system. And I just want to tell you one of the things that what our system can do today. This is only one example. We have examples from materials and so on. Doesn't matter, really. What matters is we took this problem, and we have a protein target, and we have this parent compound, and we said, okay, all we want is for you to improve on how that drug works against this target. And we used the gradient-free generative model, generative approach that I developed, co-developed during my postdoc called Stoned. We were in Canada, so I guess California is also fine. And we used a machine learning model for the docking, and then we ranked those candidates. And the prompt is simple. Based on this is the prompt from the user, not the system. You're a highly intelligent biochemist. Your job is to identify therapeutic analogs of this molecule. And this video here is very accelerated already with the chat. We have this either in fully autonomous or conversational, depends on how human scientists want to deal with it. I would say that both are okay. Really doesn't matter as long as you get to your goal. And it starts by searching the protein and gets the PDB of that protein. And then it does the docking studies. And later on, you will design the syntheses for how you would make those analogs and write the code to run those syntheses in one of the robots that we have in my lab. So some conclusions here. We developed this intelligent system that can autonomously plan, design, and perform complex chemical experiments. We're expanding co-scientists for autonomous experimental optimization campaigns, and we are developing this operational system for autonomous scientific research. So our new preprints and apps are coming very soon. Catnip is out, and some of the other things are out. I would like to thank all the agencies and everyone, collaborators that have given us funding. I want to point out Berkeley Lab here because Sam Blau is a very amazing collaborator of ours, and I didn't have time to talk about our work, but Sam is going to be here in the afternoon, or the next section. It is the afternoon right now. But yeah, we have a beautiful paper that just got accepted in Nature Machine Intelligence. And you all for inviting and listening to me. Thank you.
Have a seat, please. Okay, what'd you guys think? Pretty good set of talks, huh? Yeah, so it was a nice, for me, I will just share, it was a nice, I think, cross-section of really what we're trying to do in leveraging AI, machine learning, and accelerating materials discovery. But we also heard about some of the challenges, and what I appreciated in the talks, I think Maria and Jeff kind of both alluded to this from the beginning, that in the early days of this field, we often kind of idealized our materials. We thought of them as perfect single crystals, and we were scanning through those properties. But I think we knew it at the time, but that could only take us so far. And so you heard about, Jeff mentioned, trying to get to the device level performance. Often you're taken into some pretty messy stuff. Maria showed us all the work to characterize the defects in the interfaces, which we know are absolutely essential often to the performance of the materials for energy-related applications. And then we heard from Gabe how, rather than kind of thinking about trying to do this from sort of microscopic models and going up, you're really turning loose the techniques of autonomous systems, so building in AI and so forth, and really going on a campaign to optimize the materials and to use the feedback real time. So it's a very exciting field, but there's still a lot of challenges, and I think one of the things that I wanted to start with, and then we'll open up for questions, is just, from the perspective of the diversity of problems you guys have been working on, where do you see the biggest gaps? Like if you were a funding agent, right, or a person with a lot of federal funding, and you could put it, invest it. What would really be the one that you think would have the big impact? And beyond that, would it be the right role to focus on in academia, in national labs, or in industry? Okay. So, because I think one of the things about this field is that industry is leading in some of the areas, right? The national labs are doing heroic things, I think, in the data and many, many other things, the experimental techniques we heard about. But then I think it's sometimes we still need the theory. We still need to know what questions we're asking, and I think academia is often playing a key role there. So that's a little bit the framing here. So, all right, so I'm gonna, maybe Jeff, do you want to start as the person who actually controls a little bit of money up at LBO?
I really wish I control no money, but anyway, I should just. Yeah, it's a really good question. I think it seems like a real commodity is data, and I think and I was just kind of reflecting on that with seeing these other great talks, and wonderful to see this, and how, first of all, in our community, and maybe just defining the community as materials and chemistry broadly, there's not something similar to the Webb telescope database, or often not communally shared, kind of databases where there are kind of defined practices for where everyone can access and use them at certain levels. So one way we access data, I guess, is just mining the literature, and that's one way we get our hands on other people's data. The other one is, but we have these kind of unique experimental facilities that, are with a lot of data that isn't available and around, and so I think that is going to be very precious moving forward. It's not clear that that will be something that will probably set us apart and make us unique, even as industry kind of ramps up all of the tools that they're doing. And I would just say a microcosm of that, I think, is something I've experienced in my own kind of work, and which is that while I haven't given up on DFT, by the way. I just want to say, but I think what I think what I do is I get a foundation model off the shelf, and often it doesn't really do what I want it to do. But if I add data and refine it, then and including data that I know the provenance of, maybe I collected, maybe I generated, then I can kind of get to a point where I have something, specific that I can do what I want with it. So anyway, I think there is some. So I think data would be one thing that, and investing in tools that will generate it, store it, developing, some framework for shared data would be important.
Thank you, Jeff. Gabe, you want to go next? Or?
I will. I think that that's a great point, but I also think that that is bound to happen, and it's already happening. At least when it comes to computational data. What I do believe is that investment is needed for democratization of hardware that allows for us to collect high quality experimental data in diverse environments and diverse fields. And that is much, much more complicated. What my group does is essentially, well, we just take off-the-shelf things and modify them and break them a lot to be able to get the kind of experimental data that happens there. But in the end of the day, chemistry, material science, biology are experimental sciences that we need to have experimental validation for. And by the way, I'm a computational chemist from computational organic chemist from the beginning. But
That's okay.
thank you.
We all move in sheep's clothing.
Yeah, but the reality is that even for taking foundation models and pre-trained models and then doing fine-tuning, you want to benchmark against the real world. Yeah. And there's another point to this that I really believe in. I hope I'm wrong, but it seems like we are reaching a wall on the pre-trained models of the general purpose foundation models. And what I mentioned earlier about generating data sets of large scale, extreme scale like that is also my way of thinking that it's a way for us to get out of that wall or continue with the pre-trained models with high quality data that there is full provenance for, right? There is a reason why, as good as retrosynthesis organic models are there, they're not great, and they make a lot of mistakes because the data that's used for those is very biased. It's always often based on USPTO and patents. I can write what I want. So I think that having organized data that is standardized, the U.S. did that in the early 1900s for manufacturing, and it worked out great. We need to do something like that now, but I think that's happening. The question is how do you get that data?
Thanks, Gabe. All right, Maria, get the last word on this one.
You should write this date down. You asked 3 different scientists a question, they agree with each other entirely. That's not very common. Yeah, no, absolutely. There's data, there's metadata. So actually I can give a plug. In the MLS Bulletin 15, 20 days ago, there's an article that came out on metadata standards and laboratory information system. There's an organization called MARTA, Materials Research Data Alliance, and those working groups, and I was part of it. And we just went into a lot of details about what information is needed for the data to be useful. A spectrum is nothing without the proper metadata. And then the corollary of that, how do you enable people to actually capture all that metadata? That's the laboratory information system. So rather than, if I had any kind of power, I would make people use LIMS. Don't give me any power.
All right, great. Well, as you said, we heard a lot of agreement around data. Okay, we're going to open it up to the audience now. Yep. Do I have a microphone? Yes. I will walk around with the microphone. Okay. Oh, we do? Okay, great.
Okay, so thank you to all 3 of you for a wonderful set of talks. I've learned an enormous amount. I want to get back to machine learning potentials. So I've talked to a number of my colleagues, and one way of doing this is to collect everything you can from the literature that has the word or the letters DFT in front of it, and then use that as your basis for machine learning. But we know, those of us who've done DFT, that it depends on the functional that you use, and the functionals are cooked up for various situations and optimized, but they're not optimized for everything. The other school of thought says, I'll use machine learning to optimize the functional. and test it against experimental data where I can find it, that subset is much lower. So the question is, if my objective ultimately is to have a machine-learned potential that faithfully reproduces the physical world, what's the best strategy?
Both. I mean, I don't know. We're all, as you said, wolves and sheep. I don't know if I should answer first.
That's like almost like asking what's your favorite religion.
Yeah. I don't know.
No, there's reality. It's not a, this is not religion.
No, in all seriousness, I think it depends on the goal. I think that if we learn anything from the bitter lesson is that scale really works. So maybe, the way to go is that way. But at the same time, we do not have that kind of data at scale in a way. I mean, we'll see 24. What is it? What is the name?
What are you?
You talked about from Meta.
Oh, OMAT. OMAT.
Yeah, it is.
So, if I may, you're familiar with MatBench, the materials MLI machine learning potential benchmark, and it is, and you'll hear a lot more from Gabor tomorrow. The fact that different people care about different things. So, MatBench was developed with the materials project. People who are very interested in finding low energy structures, thermodynamics. So that's the primary benchmark. But there are people who want to look at dynamic simulations. They want different properties, and the beauty of that is the different metrics are not fixed weighted. Basically, you can choose what metric you find more important to determine which of the force field is more accurate in that parameter. And I would agree. I would really advocate for more columns. Right now, it's really phonons and energetics, right? What about other properties like charge transfer, which most of the force fields don't have, but eventually we'll need them. So that type of information, physical information of relevance to your problem, I think that's the part that should be included.
So I can be specific to help focus the discussion. I'm interested in catalysis, both from gas to solid, but also electrochemical systems, which are much more complex. But even for gas to solid, there are very limited cases where you can predict something from density functional, put it into a microkinetic model, and calculate things that you see experimentally. So I want a machine-learned potential that will do that faithfully.
Yeah, maybe.
We're going to have one closing thought on this question so we can move on.
Okay,
to
yeah.
Go ahead.
Okay.
I would just go back. I wasn't being facetious. I think one has to develop the functional and keep working on that, and one has to develop the machine learning architectures and models. And I think both of those are necessary.
Great, thanks. Okay, there's a question. I think you had your hand up before, right? Yeah, okay. And we'll let you have the last one.
Yeah, I've got two questions, mostly for Dr. Neaton. One of which is a clarifying question. I don't think I fully understood one of the things that you talked about. It sounds like the MLIP models that you're using are trained on density functional theory values, which one of the shortcomings of DFT is that it doesn't do a good job of taking into account long-range lattice distortions or imperfections. So given the fact that you're trying to correct for that, how does the MLIP model account for that? Was that one of the blue terms that you had on your slide? I just wanted to clarify.
Well, good eye. Really good eye. I would just say a couple things, and here's where the professor comes in, and so apologies. DFT is an exact theory, so actually it does include all long-range interactions if you have the exact functional. Of course, the approximate functionals that we use may or may not model those long-range dispersion interactions very well. Some of them do a decent job in certain cases, some are terrible. What we found in this situation, I think you're referring to, and check me on this, but is that we wanted our neural network potential model did not explicitly, although the DFT data that went into the model does have long-range interactions, the model didn't have an explicit representation for that. And we found that adding that improved the ability for us to come up with a good neural network potential with less data.
Got it. Okay. And then, sorry, one more quick question. It sounds like with the MOFs that you were experimenting with, you were doing chemisorption as it binds to the amine group. How do you regenerate it? Like, how do you get rid of the CO2?
You have to heat it up. Yeah.
Okay.
Yeah, and then all heck breaks loose sometimes. Yeah.
Okay. Got it. Cool. Thank you.
Okay, thank you. So I'm Boyu. I'm actually a postdoc at BIDMaP, and it's a very nice symposium that I have a chance to talk with experts. I really want to ask one question, and which is about the future direction, hardware versus software. And the question is, we know that for AI and all of the automatic things, the algorithm have developed so fast that we can use generalized or foundation model and then to pre-train. It's now the future. However, for hardware, I mean experimental hardware, and everything is specialized for a certain type of reaction, inorganic, crystal growth, or even like an instrument to detect all of them. So how do you guys think about breaking the bridge between the versatile software versus the very, very specialized hardware for experiment and even for like instrument?
I think Xi Jin's going to talk about that later. Do you want to answer? I mean, you can.
I'll give a brief note. I'm not taking the time from like the panel. In short, I think hardware can also be versatile. It's the time for us to design new hardware that is AI compatible.
That's great. Thank you.
Okay. I think, are we at time? Or do we have time for one more? I think you can ask one more. Okay, maybe one more question, and then I do want to leave enough time so that you have more detailed questions you can ask the experts here afterwards. So we'll have this be the last question.
Thank you so much. It's like I'm actually interested into several topics, but first one is like the data consistency and accuracy. It's like you use the data to train, right? And you get it from publication. Actually, from different labs, they have different gauge. It could be very different, yeah. And like from Maria's experiment, like you get diffraction map accuracy to around 85%. So what is the difference between 85% to perfect, like 100%? Can we tolerate that 15% difference and still use it, like, applicably? And another point is like, so we know AI is different from computation because AI can make decisions. So it thinks. Sometimes we don't even know how it thinks, like ChatGPT. And so like it might miss a path, the path we think about it. And so if it miss it, so are we able to know it? And are we able to design like checkpoint, like to verify like it missed or not? Like eventually, like all these models, can we generalize it? I mean, there are different models I know, but they are based on atomic models, and eventually like probably like morphs, polymers, or catalysts. They might be fall into the same models, like if everything could be gauged. So can we do that? And the final question is like, in the future, we want property to structure, which is inversed. I mean, structure to property, which is nice, but eventually we want property to structure. Like I want room temperature superconductor. So what is a structure? So that's what I'm interested in. Thank you so much. Yeah.
That's a lot.
That is
That's
the
lot.
field of
There we go.
materials discovery.
Okay, just quickly a couple of the points. Data consistency. I would argue that you do not use literature extracted data, to do like the only training if you want one model. You could seed it to do autonomous experimentation. You could augment it to computed data. Most of the time, we use data that we extract on a one-off from separate sources, more as a gold standard to validate, simulations or test the models, rather than use them, combine all of the hodgepodge to do machine learning training. So that's one point. The second is, I think you asked, that might be your third point, but I don't think we can answer all of them. It's really enticing to think about whether you can have a foundation model for all types of materials. And I don't think that people have an answer for it now, but there is certainly a strong desire to have, you know, a model that works to predict properties for molecules, for MOFs, for polymers is its own world of devil. I don't know. But the problem is the scale, right? You know, the things have different length scales, so you have to figure out how to combine them, and that is a long-standing problem, I would say. And I think the final question is actually probably the easiest. If you have a way to sample the space of possible structure, and you have a very good structure to property predictor, the inverse problem is solved.
I just want to put I don't know, a point here that connects the two questions, the hardware and this one. Yeah. The hardware one, I really tend to think that, you know, these are tools. The models we're building, these are tools. The problem, the question that we really have to be thinking about is like, what do you want to solve? I think Omar would like to solve removing carbon from the atmosphere. Is that okay? Not to put words in. And it doesn't matter how you're going to get there, right? But if you can have the hardware and define the software that will allow you to ask those questions and get good answers, it doesn't matter. And similarly, does it matter? Do we need to have an oracle that knows everything about any problem? I don't think so, right? I think it's better to be pragmatic about the problems we're trying to solve.
Okay, I think that's actually a good way to end this session. So let's please thank the speakers one more time, and then we'll go into break.